Hi dear students, today we say about Gamo's theory of alpha decay. Alpha means it is the helium nuclei, that is it has two protons and two neutrons present in this alpha particle. So it is discovered by the Gamo. It is the scientist name, so this theory is called as the Gamo's theory. And then we see about this alpha particle is emitted from the heavy nuclei. Here two proton and two neutrons are combined and strongly bind, and it is from the alpha particle. Here u naught is represents the attractive potential. Normally it is the suppose it is in the one heavy nuclei, it has some radius, that is r, it is in the order of Fermi. At that time the heavy nuclei, inside the heavy nuclei this alpha particle is produced, and then this alpha particle is emitted from the heavy nuclei. It is very tedious because it has some Coulomb repulsive force and some potential is inside the nucleus. That potential is represented by the potential well, that is V of R. Here the alpha particle's energy is it is in the size, and but the potential well size is very large compared to this energy of the alpha particle. Now we have considered the equation, that is it is our heavy nuclei. In this case it is in the ground state, but it is in the unstable state, means automatically it is emit the alpha particle. It means that two protons are emitted, so automatically here the proton number will be changed, and two neutrons is also combined with the alpha particle, so automatically in the mass number 4 numbers is reduced, so new daughter nuclei is produced and one alpha particle, that is helium nuclei, is produced in this equation. So the potential energy is general formula Q1 Q2 divided by 4 pi epsilon naught R. Here in our case, here two proton, that means two charged particle, that means it is 2e, and Z minus 2 of charged particles in the daughter nucleus, so Z minus 2 into E, that is one is the Q1, another one is Q2 divided by 4 pi epsilon naught R. Here the R is represents the potential well distance. Okay, now suppose the R value is greater than the radius of the nucleus. This is the general formula. Now we have considered the uranium 92-238, means automatically the values will be substituted in this equation, and we get the value 26 million electron volt. That is the potential well height is 26 million electron volt, but in the alpha particle maximum potential is simply 4 million electron volt. How to this alpha particles is emitted from the potential well? It is explained by the tunneling effect. Okay, now we have considered the interaction in the nucleus is attractive potential. So this is the internal energy is equal to the potential well energy. Okay, this is represented in this equation. It is only applicable when the small r value is less than r, that is this R is only present in this well. Suppose the small r is greater than r, means the r small r value is, that is the particle in outside the well. Okay, now we see the tunneling effect. Here suppose we have considered the one tunnel. Here that is our particle, it is moving like a wave. So it is the move like this way, that is the wave function is mu1. Suppose it is moved to the tunnel, I mean move through this tunnel, automatically the wave function is represented by u2, and it is outside the tunnel, automatically the particle is moving like a wave, the wave function is u3. So here the region is 1 and region is 3, it is region is 2, because region 1 and region 3 both are the same region, but in the region 2 it is the another one barrier region. Okay, so here the particle is incident on the barrier, automatically it is in this arrow mark. At the same time this particle is reflected in the barrier, it is represented by the opposite direction arrow mark. In the same way, the particle is moving through the barrier. Automatically it is in this direction and it is reflected by this wall, is denoted by this arrow mark, and it is transmitted in the transmitted to the region 2 to the region 3 through the, so it is only in this direction. So we have already know this Schrödinger equation, minus Kirchhoff square divided by 2m del square psi plus v psi is equal to e psi. So this equation is remodulate, and then remode of equation is in region 1 and region 3 both the region the equation is same. So d square u by dr square plus 2m by h cross square eu is equal to 0. Here the potential is, there is no potential, so it is the potential value is 0. So in our case we have considered 2me divided by h cross squared is equal to simply k1 squared. So automatically it is k1 squared u is equal to 0. Okay. Here the m is represented in this equation is the reduced mass, because in our case both the alpha particle as well as daughter nuclei both are produced in this equation. So m is equal to m alpha md divided by m alpha plus md. So it is our equation number. Then the region 2, the Schrödinger equation, it has potential is involved, because in this Schrödinger equation here some barrier is there, so automatically it has some potential. So the value of potential is represented by V, and then it is rearranged. So that means the minus sign is taken outside, so V minus E into U is equal to 0. This 2m by h cross squared B minus E is denoted by K2 square. So the equation is rearranged this form. Okay. Now the solution of equation 3 and equation 5, it is in the following equations. First in region 1 and then region 2 and then region 3, like that. First in region 1, the solution is, the wave function is u1. So here the solution of this equation is represented by u1. At the same time, here's two type of waves are there. One is incident wave, another one is reflected wave. So in this case it is plus k1 squared. So automatically in this equation exponential of ik1r, because it is represents the sine wave. Okay. So cos I plus cos kr plus I sin kr. So it is simply exponential of ik1r plus b1 e I minus ik1r. Okay. So in our case k1 represented by, already we know that it is simply k1 square is equal to 2mb by h cross square. So k1 means it is root. Okay. Now we have considered the second region. There is no wave functions. So in this case only transmitted wave is moving. At the same time it is reflected in the another wall. So automatically it has also two terms. One is, it is only represented by e power k2r and e power minus k2r, and there is no imaginary part I term. Okay. So here k2 is represented by square root of 2m v minus e divided by h cross. Okay. In the region 3, the transmitted wave, here only one direction the wave is moving, so automatically it has only one constant, that is a3 into e power I k1r, because the equation is same for region 1 and 3, so it is simply k1r. Okay. So here 5 type of constants are there. In first equation a1 b1, and second equation a2 b2, and third equation it is a3. So these 5 equations are solving by using the boundary conditions. Now we see the figure. It is r is equal to 0 and it is the point. It is r is equal to a. Now we have considered at r is equal to 0, two type of wave functions are there. One is u1 and one is u2. So both the wave functions are connected at r is equal to 0. At the same time, at r is equal to a, u2 and u3 both the wave functions are connected. So at r is equal to 0, u1 is equal to u2. At the same time, the first order differentiation is also equal. So dou u1 divided by dou r is equal to dou u2 divided by dou r. So these are the boundary conditions for at r is equal to 0. At the same time, r is equal to a means U2 and U3 both are connected, so both are equal, and the first order differentiation of these two wave functions is also equal. So already we have write down the values of u1, u2, u3. So these values are equated in the and substituted in the above equation, that is the boundary conditions. Okay, first of all, u1 is equal to u2. So u1 equation is there, and which is equal to u2 equation. It is only for r is equal to 0. So automatically the value of r is replaced by 0. So e power 0, anything power 0 is 1. So this term is 1, and this term is 1, this term is 1, this term is 1. So a1 plus b1 is equal to a2 plus b2. We get the one equation. Then the corresponding another one boundary condition, dou u1 by dou r is equal to dou u2 divided by dou r. So in our case, this value, that is u1 value is differentiated. So a1 is the constant. So simply it is a1, and it is b1. Okay. And then e power ik1r, it is differentiated. So e power ik1r. Then power is differentiated, simply ik1 into 1. So ik1. In the similar way, this term is also differentiated, which is equal to this term is differentiated, and this is also differentiated in this equation. Finally we get the answer for at put r is equal to 0, and the exponential terms are equal to 1, remaining terms are there. So it is equation 13, and it is equation number 14. In the same way, the boundary condition u2 is equal to u3, and u2 dou u2 divided by dou r is equal to dou u3 divided by dou r. Both the equations substituted, and the values of r is equal to a is also substituted, and we get u2 is equal to u3, means automatically the equation is equation number 15. So it is u2 equation, and it is u3 equation, and the value of r is replaced by a. Okay. Now dou u2 divided by dou r is equal to dou u3 divided by dou r. So the equation is differentiated, that is u2 equation is differentiated, we get the equation, and u3 is equation is also differentiated, we get this equation. After that, the value of r is replaced by a, so we get the another one equation, it is equation number 16. Now equation number 15 and it is 16. Okay, both the equations we get, it is equation number 15 and it is equation number 16. So in this case, the above two equations are solved simultaneously. So the equation number 15 is multiplied by k2, so we get this equation, and it is equation number 16, and so these two terms are cancelled out. Finally we get the value of a2 from this equation. So in our case, it is modified like this, because this denominator exponential term, it is moved to the numerator, automatically it is get minus sign, and we get the value of a2. In the same way, this 15th equation is multiplied with k2 and rearrange the sign in the 16th equation, automatically we get the value of b2, and it is rearranged like this. So these two equations, that means a2 and a3, a2 and b2, both the values we have calculated using the final two equations. Okay. In the same way, equation 13 and 14, both the equations are solved by using the simultaneous equation method, and automatically we get the solution for the a1 in terms of a2 and b2. Already we have calculated the value of a2 and b2 from the previous calculation, that is equation number 17 and 18. These two equations are substituted in this equation, and then the values are substituted in this equation. It is equation number 19. Automatically we get the a1 in terms of a3 and some other terms. Okay, normally the velocity of alpha particle in the region 1 and region 3, both the terms, the velocity is equal, but in the region 2 the velocity value will be changed, because the region 1 and 3 is the same region, but it is the incident way, and it in the region 3 it is the transmitted way. It is only main difference. Otherwise both regions are the same, but in the region 2 is not like that, it is the another one region. So the transition probability of the incident alpha particle is calculated. This is our aim. So transmission is calculated by using the formula transmitted flux divided by incident flux, because both the regions, the 1 and 3, have the same velocity. So we have calculated the transmitted flux divided by incident flux. So this is the formula, modulus of A3 squared into V divided by A1 squared divided by V. So here V represents the velocity of alpha particle. It is cancelled out. Simply it is A3 squared divided by A1 squared. Now we have used this formula. A1 divided by A3 is calculated easily from this equation. So first we have calculated A1 by A3 the whole square. So it has some imaginary terms over there. So automatically in square means it is A1 by A3 into A1 by A3 star. That means conjugate of this first term. So both are multiplied. We get the value of A1 by A3 the whole square. Okay. First A1 term divided by A3. So in this equation the A3 term is common in both the terms. So taken outside and simply the remaining terms are there. Okay. Then after that A1 divided by A3 means it gets one equation. So A1 by A3, this equation, it is squared means automatically this term is squared. So square means automatically we have known one that that is this term into another one term. That term is simply the conjugate term. So in our case we have used the formula, that is A plus B the whole square is equal to A square plus B square plus 2AB, because normally A plus IB the whole square means the general formula is A square plus B square. Simply this is because this means it is A plus B, that is A plus IB into A minus IB. This is the equation. So automatically we get A square plus B square. But in our case it is square term. The plus there is no I. In the individual term, in the bracket, the imaginary term is there. So we have used the formula A plus B the whole square, that is A square plus B square plus 2AB. So first term is square. So 1 by 4 is square means 1 by 16. Then 1 plus IK1 by K2, this term is square. And then this term is square. Then this term is square. So in the power 2. In the similar way, this term is square terms. Then 2 into first term into second term. So here the first term, this is 16, and then square. Square means automatically it is 1 plus IK1 divided by K2 into 1 minus IK1 by K2. So it is using this formula. So answer is A square plus B square. So simply 1 plus K1 square divided by K2 square. And the same formula is used in this equation also. So we get this equation. And then it is the power term. So e power 2 IK1A minus e power 2 K2A. So this is like that. In the similar way, the second term and third term both are written in this case. And then the last term, the exponential terms powers are cancelled out, simply e power 0, so it is 1. Okay, so these are explained in this case. And the same time e power 2 ika 1 means it is calculated in this way, that is e power ik1a is the whole square means automatically this equation is written like this. So it is cos k1a plus I sin k1a the whole square. Already we know that whole square means this is the conjugate term. So a plus ib the whole square means a square plus b square. So automatically cos square plus sin square it is equal to 1. So this term is 1 and this term is 1 and this term is also 1. Simply these two terms are there. So it is in this, it is represented in this equation. That is, it is the first term and then second term and then third term. The common term is the 16, 1 by 16, 1 plus k1 square divided by k2 square into 1 plus k2 square divided by k1 square is the common term for these three terms. So taken outside, simply e power 2k2a plus e power 2 minus 2k2a plus 2. So this is the simply e power k2a plus k minus k2a the whole square, because e power x plus e power minus x the whole square means e power 2x plus e power minus 2x plus 2 into e power x into minus e power minus x. The same equation is there, so it is simplified like this. In this case, this e power 2k, I mean e power k2a value is very much larger than compared to the 1. So automatically it is the negative sign, means it is very small when compared to the 1. So automatically this term is negligible. So simply it is e power 2k2a. So simply this equation is e power 2k2a. Now this terms are LCM taken in this terms. So it is k2 square plus k1 square divided by k2 square. Here k1 square plus k2 square the this term. Here in the numerator k1 square plus k2 square is the common. So it is square, and then denominator k1 square into k2 square. This is the a1 divided by a3 the whole square, but in our case we have calculated the transmission a3 divided by a1 the whole square, so it is take invert. So the equation is like that. So in this term the part is usually the magnitude value of alpha particle is 4. It is the maximum value. So it is very high for the alpha particle, but at the same time the potential well is very large. It has 26 million electron volt. It is simply 4 million electron volt. It is very small value. How to the alpha particle is escaped from the potential well, that is escaped from the nucleus, means it is very tedious one, but the factor is simply 4, means simply we use the exponential term. So the potential is very much large, that means very height when compared to the energy of the alpha particle. It is represented in this figure. So the well is very high, so the alpha particle is tunneled it formed the hole and moved through the potential well to outsides. Okay, so this is the energy of the potential energy, and the energy of the alpha particle is represented, and here the alpha decay, this type of decay is called as the alpha decay, because alpha particle is emitted. So the probability for produce the transmitted from the potential well to outside, it is the exponential term. It exponential of minus 2k2a. So here we get the total number of energy, that is transmission probability is measured by using the equation, next equation, that is t is equal to e power minus 2 k2 into dr. Here V is very much greater than the energy, that is potential energy is very much greater than the alpha particle energy. So V is due to the Coulomb repulsion. So automatically the transmission waves is means automatically the exponential of minus 2. K2 value is already we have know that. So that value is substituted in this equation. This is the equation number 23. So now we have some assumptions is produced. We have considered some assumptions. First one is the alpha particles is moves inside the potential well have some certain velocity. That means the velocity value will be constant. It is the first assumption. And hits the wall means automatically the velocity value will be changed as V0 divided by 2r times per second. So automatically the alpha particle probability T landing out of each hit. So escape velocity, escape probability is measured by using the some decay constant. That decay constant is represented by the term lambda. So V0 divided by 2r into this exponential term. Okay. The unit of the decay constant is second power minus 1. Okay. Now we have considered another one. The speed of alpha particle, it is in the order of 10 to the power of 6 meter per second. At the same time the radius is in the order of 4 me. It is the normal one, but in the heavy nuclei it is very high. So it is 10 to the power of minus 14 meter. At the same time the alpha particle will find itself the exterior surface of the nucleus. So 10 to the power of 20 times per second. So the actual value of decay constant, that is lambda, For thorium is 10 to the power of minus 18 second power minus. The probability range, that is escape range, may be 10 to the power of minus 13 to 38, minus 38. So now we get the logarithm of this equation. So log of, that is, it is natural logarithm. So logarithm of E, lambda is base E. Okay, so that is both the terms are multiplication. So the log of this term plus log of this term. So automatically the exponential and log will be cancelled out. Simply this term is there. Okay. Now it is the log terms. So in our case, V of R is represents the potential well value. So it is simply 2 into Z E minus 2 E squared divided by 4 pi epsilon naught R. Already we have know the value of potential well. So this is substitute in this equation and we get this equation. So here we have consider the energy value is simply represented by the 2 into Z minus 2 E squared divided by 4 pi epsilon naught into R1. Here the E is moved to the outside because move to the outside in the next term, because in the outside E is represents the constant value. So here we use the it is in the use the term R1. So the upper limit is all R1. Okay, so the suppose we have calculated the upper limit, means using this equation we get the value. So now we have consider R is equal to R1 cos squared psi and R is equal to capital R. It is the lower limit, that is R1 cos squared psi naught. So from this equation we calculate the value of psi naught psi like that. So these values are substituted in the above equation. So the values are substituted and the constant terms are taken outside. Finally we get this equation. So here simply lower limit R, upper limit R1, and it is R1 because 2 Z minus Z E squared divided by 4 pi epsilon naught R into E. So these terms, the R except R, remaining terms are equal to R1. So the is 2 into Z minus 2 into E squared divided by 4 pi epsilon naught E is simply R1. So it is taken outside like a R1. Now the lower and upper limit are replaced by the term psi. So the limit will be changed as psi naught, and here it is 0, and the term is simply plus 4 into square root of 2me epsilon divided by h cross. So here in the integration term, it is sin square psi into d psi. Already we know that cos 2 theta means it is 1 minus 2 sin square theta. So sin square theta means automatically 1 minus cos 2 theta divided by 2. From this equation we have using this equation we replace sin square psi is replaced as 1 minus cos 2 psi divided by 2. So in the equation log base E lambda is replaced like this. So this term is integrated, we get psi minus sin 2 psi divided by 2. So substitute the upper limit minus lower limit. So this equation we get. Okay, now we have calculated the value. This is our equation. We know that it is sin 2 theta. So sin 2 theta means 2 sin theta cos theta. So 2 cancelled out. Finally we get the equation like that. So already we know the value of cos squared psi is R divided by R1. So cos psi naught means automatically it is taken square root on both the sides. At the same way, from this equation we have calculated the sin naught. From the equation cos squared psi means this term is sin squared psi means 1 minus cos squared psi. So automatically 1 minus this term. From this equation we have calculated the sin psi naught. So these values are substituted in the above equation. Finally we get the equation like that. So in this equation we have considered the value of capital R, that is the radius of the nucleus is very much less than the value of R1, means automatically we have considered this first term cosecant inverse term is replaced by 1 by pi by half, pi into half minus R by R1 the whole power half. At the same time this R by R1 is compared to the simply 1 minus of R by R1 the whole power half is simply replaced by 1. These values are substituted in the above equation, and finally we get this equation, and then it is simplified like that. Okay. So this is our calculated equation. here it is the bracket terms are multiplied with these two terms, so we get this term. In this term common terms are cancelled out, and finally we get the equation. So here the values are substituted and it are combined, and E and R1, it means it is R1 value is already known, so it is cross multiplied. So ER1 means simply this value, it is substituted in this equation, and then finally we get, it is simplified, and finally we get this equation. So it is the final form, log of V naught divided by 2R minus E square divided by H cross epsilon naught M by 2 the whole power half Z minus 2 into E power minus half plus 4E divided by H cross into M by pi by epsilon the whole power half R power half Z minus 2 the whole power half. Now we have considered Z minus 2 is simply represented as the doctor nuclei. So Z of D is equal to Z minus 2, and then remaining terms or constant terms. So substitute the value of E, M, and then values. Finally we get this equation, and then suppose it is the natural logarithm. So it is normal logarithm means it is divided by 2.7 or 3. So we get this equation. Okay. So here some assumptions are there. This equation is only true for the ground state nuclei in the, because it has, there is no angular momentum terms. Suppose it is in the excited nuclei means it has angular momentum is involved in this derivation part. So automatically in this equation, in the previous one, that is in the integration term, the angular momentum term, that is L into L plus 1 divided by 2mr squared into H cross squared, that term is involved in this equation, and then the same derivation is there. So it is very tedious. So we have only explained in this term only the ground state heavy nucleus is emitted pre-excited alpha particle, and then we finally we get the value of decay constant, and that is the logarithmic term of decay constant. Okay. At the same time, in this decay constant, it is the spontaneous disintegration means automatically the gamma factor, that is also one is produced, that is represented by e power minus gamma. So it is only for the heavy nuclei in the ground state. Okay. So the Q factor is also calculated by the same way. Q factor value is similar to the potential well value. So potential will value, that is V is equal to 2 into Z minus 2 into E square divided by 4 pi epsilon naught R ன்னு போட்டிருப்போம். The same way here Q is equal to 2 into Z minus 2 E square divided by 4 pi epsilon naught A. So the value of A is simply 69.8 Fermi for lead. Okay. So this type of this is only applicable for the Q factor for in the heavy nuclei in the ground state. Okay. So automatically our Q factor's value is simply, the numerator is same, that is Z minus 2 into E square divided by, but denominator is 4 pi epsilon naught, the R is replaced by A. Okay. The A is normally the radius of the nuclei, that is 16, it is in the order of 4 meters. That is 10 to the power of minus 15 meter. Okay. Maybe the value will be changed. It is in the order of 4 me. Finally we get the value of transparency, and high mean lifetime is also measured by using this gamma theory. Okay. Thank you.